Let's review what we know about linear regression so far. First, the equation of a line that goes through the origin, 0, 0, is y equals r times x. R describes the slope. For every 1 you go to the right, you go r up. A more general equation of a line is y equals rx plus b, where b is the intercept. When x is 0, a point on the line is 0, b. The slope has the same interpretation as before, and every point on this line will be described as some x, some rx plus b. In standard units, the regression line is a line through the origin. A typical use for this line is to give you an estimate for y given some value for x. So if x is 1.5, the line would estimate that y is 3/4. In this case, we've drawn a regression line with a slope of 0.5. The slope of the regression line in standard units is always the correlation coefficient r, and that's some number between -1 and 1. In original units, we really have the same scatter diagram, except for we haven't centered the axes onto the middle of the diagram or scaled the axes to make sure they match with standard units. Instead, we're measuring the position of each point in terms of its original units, points on an exam, or inches of height, or whatever. It's really the same scatter diagram over in original units, it's just everything's position is described in a different way. And it's the same line, but now we have to describe this line in terms of original unit positions as well. And so, this is a line that instead of going through 0, 0, goes through the average of x, average of y, and its slope is not just r, it's r times the standard deviation of y divided by the standard deviation of x. So if you're dealing with values in standard units, you only need to know one number in order to draw the regression line, and that number is the correlation coefficient r. But in original units, you need 5 numbers: the average in SD of x, the average in SD of y, and the correlation coefficient r. Once you know these 5 numbers, you can describe this line. And when there's a linear association between x and y, this line will give you a reasonable prediction for y given any value of x. Shifting from diagrams to equations, in original units the regression line has the following equation: y in standard units is r times x in standard units. And what does it mean to be in standard units? Well, that just means you've subtracted off the average and divided by the SD. So this is actually an equation of the line in original units, even though I've written standard units down here. Y here is measured in original units, points on an exam, inches of height, or whatever, and so's the average and so's the SD. Now this expression of the regression line is inconvenient because y is not isolated on the left side of the equals. Isolating y on the left side of the equals means that we'll end up with some slope times x plus some intercept, where again y and x are measured in original units, whatever they came in when you measured these values in the first place. And the way we figure out the slope and the intercept is just by rearranging terms in the equation above. So we move the SD of y over by multiplying and move the average of y over by adding. What you end up with is that the slope of the regression line is r times the SD of y divided by the SD of x. And the intercept of the regression line is the average of y minus the slope times the average of x. Now the slope here is just the slope of the line. We looked at that in the diagram before. The intercept is what you get when you start at the center of the scatter diagram. That's the average of x, average of y. And you move along the regression line until you reach x equals 0. And one useful observation about this expression is that the slope tells you how much your estimate for y changes as x changes. There must be some correlation between x and y in order to change your estimate of y given a change in x. If x and y are uncorrelated, they have nothing to do with each other, then you just guess the same y all the time because learning something about x wouldn't tell you anything new, so you might as well just keep your guess the same. So if r is large, meaning these are highly correlated, then you would expect the slope to be large as well. But the slope is only large if the SD of y is large. The y values you're trying to guess have to have some spread to them for it to make sense for you to pick different y predictions for different values of x. And the slope of the regression line is only large if the SD of x is small. SD of x being small means that the x values are not too spread out. That means one change in x value is a big difference. Whereas if the SD of x is large, the x values are really spread out, then little changes don't matter as much when you're trying to predict y.